So I think we can start. Welcome everybody. Welcome to the IAPS seminar, the weekly IAPS seminar. I'm glad here to have here as today's speaker, Nicolas Peretto from the University of Cardiff. I will leave the introduction to Alessio Trafficanti here that he will introduce today's speaker. I just want to recommend people that want to raise any question to the speaker to wait for the end of the seminar. And for people attending online, they can raise their hand or write on chat, and we'll give them the possibility to interact with the speaker. Thank you. Alessio, the floor is yours.
Thanks, Eugenio. It's a pleasure for me today to introduce Nicola Peretto and his seminar here. So Nicola is an old colleague of mine, is a very good expert of the star formation field. I actually think we just discussed that before, that the first ALMA data is an expert also of ALMA data. The very first image ever taken with ALMA in cycle 0 were taken for resource SDC35, that probably will appear also in some of these slides, so we'll see. So he got his PhD in 2005 at CA in France, in Paris, and then he moved in Manchester, working with Professor Gary Fuller, which is also a guest of us today. And then in 2009, he moved back in France with as a Marie Curie co-found fellow until 2013, when then he moved as a lecturer in Cardiff, where now he's a reader. Okay, so that's all for the presentation. The floor is all yours, Nicola. Thanks for coming and enjoy.
Yeah, thank you. Well, first, thank you for having me here today. It's a pleasure to be here, even though the weather is not that great, but used to it. Some of you might wonder, I get that quite often. Yes, my name is Italian, but I'm not Italian. I have some Italian heritage from both of my parents, but as you know, no one is perfect. Anyway, today I'll be talking about star cluster formation within molecular clouds, cell-penetrating molecular clouds mostly. So just to make sure that I know that in the room, that's gonna work. No, it doesn't work anymore. That's okay. Just to make sure that we all on the same page and we understand the word that I'm using and in which context. I'm stepping back a bit and have a short introduction on the type of structures I will be talking about. So here we have a well-known galaxy, N51. You know, all of you have seen these beautiful images of HST. In terms of size, mass, and so on, is not too dissimilar to what we think of the Milky Way. It's a grand spiral design, and it has a similar kind of size and so on.
Sorry. This. Oh, doesn't disappear. Sorry. I wanted to shut down that.
It's okay.
Was not. Sorry for that.
I see. Yeah, here I can't have X. Wait.
Because
No, that's. I don't think that's
no.
linked to this.
No.
Anyway, so as I said, similar to ours, what we can see on this image is a number of structures. Obviously, the spiral arms are quite prominent. As we can see, there are some red stuff here. These are young massive clusters forming along the spiral arms mostly. And associated to those arms, you can clearly see these dark lanes. This is coal dust, which is absorbing the background light, and that's why they appear dark. And there's clearly a correlation between the presence of the star clusters forming and the dark lanes. And in fact, if then you look at the same galaxy, but this time not in the visible with HSC, but in molecular lines. So this is carbon monoxide, the 1-2-0 transition, data from Schneider et al. In 2013. You see there's an excellent match between whatever you see as along these parallels, dark lanes, and the CO molecular cloud structure. So here you can already see that the direct link between the presence of coal dust, because to be able to absorb the background light, you need to have coal dust, star cluster formation, and the presence of molecular gas. Right. So now if we zoom in, and I lost my cursor. Where's my cursor? Ah, wait.
Here it is.
Sorry about that, but I lost my cursor, so I can't move slides.
Try to exit to the presenter and then. Oh, this is very stuck.
Yeah, it seems to be.
We cannot even stop the desk.
I think is completely fried even because nothing is.
Well, it was impressed by the galaxy. That's interesting.
Yeah,
So your computer is completely frozen.
yeah.
Yeah, let's. I would say let's take off.
Yeah. Okay, we are back in the game, maybe.
You have to share again.
Ah, we have to share again.
Yeah.
Oh yeah,
I'm
sorry. Not back in the game yet. Share. I need to share this one. And then I need to do this. And this.
You can.
Okay. Can I start again? Okay. So we have this link between this dark lane, molecular gas, and cluster formation, right? So now if you zoom in some of these parameters, or this is in some of these large molecular clouds structure, you might see something like that. So this is one given molecular cloud in our own galaxy. It's not M51 anymore. What you see here is that these ISO contours in white shows you the column density, so the amount of mass that you have along the line of sight at each position in this cloud. The background is a composition between Herschel, Huygens, and some radio emission. And if you look at the peaks of the column density, where most of the mass is, you have some here and here and here, you can also see that often these are associated with this orange emission that you can see in Herschel, which trace current star formation. So not only star formation happens in molecular clouds, in fact, star formation happens in the densest peaks and over densities within these molecular clouds. Okay. And more than forming within it, in fact, star formation feeds from it, right? The mass that ends up in stars, in star clusters, directly come from the mass that you see here in this molecular cloud. So there's a mass transfer between the clouds to the stars. That's what star formation is all about. So now we can even go deeper inside these overdensities. And if you do that, you might see in something like this. So here it's again, it's a 7 mm image of a nearby protocluster in Sapiens. And this is the corresponding Spitzer composite image in the mid-infrared of the same region. And so here what you can see is that in its 7 mm image that probes you the cold dust, you see these envelopes that we often call cores, right? So you have a number of them. And in fact, at the center of those, if you could do the match, you would realize that you have one or a few protostars that you can see in red here, traced in the mid-infrared, that actually directly form within these cores. Right? So you have a hierarchical structure of gas from these large-scale spiral arms where you have this cold dust and molecular glass to molecular clouds that are a few tens of parsec to clumps. That's what I call clumps here, which are about a parsec in size, to cores, which is typically 0.1 parsec or less, and protostar themselves that are of the order of below the AU size. So here, to try to justify my interest of clumps, right? So clumps being this parsec gas structure here. I show you this plot here. This is a plot from the review from Mark Remonts in 2019. where here you have the mass of stellar clusters. So these are not, they are stellar clusters. Here's the radius of these stellar clusters. And here it's for different clusters across different regions. So you have blue, this is the Milky Way, this is M31, and so on and so on. And now if you overplot in there the where clumps, so parsec scale clumps, sit within our own Milky Way. So this is come from a sample of James Huckworth and collaborators in 2018. They mapped the full galaxy, or a good fraction of the galaxy, and compiled a sample of clumps on the parsec scale. And they typically, in the mass size plot, they typically sit around here, right? And in fact, as star formation goes on, what you expect, the clusters forming in such clumps, you would expect them to then end up in that region as they necessarily lose mass, right? Star formation is not 100% efficient. So if you have a clump of a certain mass, the star cluster that will form from it will be of lower mass. And as the cluster relaxes and you lose your gas mass, they tend also to expand a bit. So typically, if you start your initial condition of cluster formation here, then you end up with clusters that typically are sitting there, right? So this clump, these parsec scale structures are indeed the direct progenitor of star clusters, and we can see that in a number of ways directly here in that particular image, but in a more general way, statistical way, through a plot like this one. Okay. That's good. So the question that drives most of my research, but the research of many people, well, in this room and also in the star formation community, is really to try to understand this mass transfer from these clouds, 40 parsec in scale, to the clumps that will form star clusters, to the stars that will form within such a clump, right? But what drives it? I mean, the physics that drives it. So we know that it's a flow, its mass has to be transferred, but what was the physics that drive that transfer is really not clear. Could be, there are models that predict that it's most likely gravity on all scales. Some say it's turbulence, feedback, magnetic fields, and so on. So in order to respond to that question, what drives the star formation flow, really what you need to do, I mean, one of the things that you can do is to try to study the detailed energy balance, turbulence, gravity, magnetic field, and so on, in these molecular clouds, and try to see if we can identify regions within these clouds that are dominated by turbulence or gravity or magnetic field, and so on. So in this talk, I will have two parts. In the first part, I will present a study of the energy balance profiles of molecular clouds. And that's basically a paper that we published in 2023. And then in the second part, I will talk about the internal kinematics of those clumps, the star cluster progenitors. And that's mostly on two papers, one by Andrew Rigby in 2024, and another one by Michael Anderson, which hasn't been submitted yet. Okay, so the energy balance. So what do we mean by that? So here we'll focus only on two elements. We will forget magnetic field for now because magnetic field is not nice. But we'll focus on gravity. Gravity, they only try to do one thing, is to collapse the gas, right? It tries to bring things together. That's the only thing it does mostly. And then you have turbulence, which is more complicated. So the impact of turbulence can bring things together through shocks and create overdensities, but it also tears the gas apart, right? So it has a dual kind of role. What we want to do is to estimate the relative contribution in the clouds, molecular clouds that form stars, between these two elements. And we do that by computing a ratio, which is called the virial ratio, alpha vir, which is estimated as twice the kinetic energy divided by the kinetic energy. And if this virial ratio is 1, this is consistent with a cloud of uniform density and a spherical cloud, uniform density that might be in hydrostatic equilibrium, so pressure gradient balancing gravity, things are not moving. It's not because you have a virial ratio of 1 that necessarily your cloud is in hydrostatic equilibrium, but if it is in hydrostatic equilibrium, you expect that kind of value for the virial ratio. Yeah. So the idea is to compute these two quantities, this EK, kinetic energy, and EG, the gravitational energy. Obviously, this is not new. People have done that for many years. And there's a number of papers. Some are quite well known. So this one, the first one I'm going to talk about very briefly is the Heyer et al. 2009 paper. And so what they've done to that plot here is to so they look at the sample of molecular clouds that were studied already before and quite known. And they looked at the mass surface density of these clouds, right? Which is in there, basically you have, it's related to the gravitational energy of the cloud in a way. And then a ratio that they derive, which is the velocity dispersion of the cloud divided by the square root of the radius. And in such a plot, clouds that have a Virial ratio of 1 should sit here on that red line. Clouds with a Virial ratio of 4 should sit on that red line there. Right? And the clouds are over here. So from that, they concluded that that was consistent with clouds being in virial equilibrium. And the reason you can see, obviously, it's slightly, the values are slightly larger than a Virial ratio of 1, but that can be explained in a number of ways. One here is only if you have a density profile which is uniform, which is not the case in molecular cloud. And also you have uncertainties on a number of parameters. So their conclusion is to say this is consistent with basically virial equilibrium. The issue is that you expect actually very similar relationships in terms of in such a plot. So clouds that basically follow a constant line of virial ratio here. For clouds that are not at all in a hydrostatic equilibrium, but are clouds that are in free fall. So if you have cloud in free fall, basically what you expect is that that's when the free fall is well developed, your kinetic energy basically is equal to your gravitational energy. Right? And therefore, such a plot, given the uncertainty of the measurements, is not really telling you whether or not your clouds are collapsing or in equilibrium. And then you have samples, a complete sample of molecular clouds in a galaxy that have been done and released in some papers. So this is a plot from Miville-Deschênes in 2017. They looked at CO data of the Milky Way, computed a sample of molecular cloud, complete sample of molecular cloud, and plotted the distribution of this virial ratio. So if you're in black here, if you look just at the black one, that's the full sample, and yellow is the inner galaxy, blue is the outer galaxy. That doesn't really matter. What matters is the values. That's a value of 1, 10, and 100. Remember, you have a cloud which is in basically self-gravitating or bound is a value of basically 2 or 3, so about here. So it seems that the vast majority of the clouds here are unbound, right? That's what it seems. So not self-gravitating. Probably there are transient structure that might just disperse if you could wait long enough to see them dispersing. So with these few studies that I've selected here, you can already see that there's a complete disagreement into what molecular cloud does, if they are bound, if they are in hydrostatic equilibrium or not, if they are collapsing, and so on. So how can we move forward in that context? So what we've done is to take a sample of clouds, and instead of having one measurement per cloud, to try to derive that profile within a cloud. So see at different radius within a cloud, we want to measure what's the ratio of the gravity versus kinetic energy inside this cloud as a function of their own radius as we go out within the cloud. And by doing this, that has several advantages, is that within the same cloud, right, independently of the absolute measurement that are uncertain, the relative variation of these measurements within the cloud should be relatively robust. So what we want is that for gravity, we want to have a mass profile, right? Gravitational energy is basically a function of the mass over the radius. So you just need to have a plot that tells you as a function of the internal radius of a cloud, its mass within that radius, and you are able to compute that parameter. And then for the kinetic energy, what you want is a velocity dispersion profile, that because the kinetic energy is m sigma squared, and therefore the m, you get it from here. You just need to compute the sigma, which is the velocity dispersion, that you can get from that. So that's the two things that we want to compute, a mass profile and a velocity dispersion profile, so that then we can derive a viral ratio profile. So that's what we've done. So to get the mass, we use a H2 column density map within. So here we have a cloud, right? You have, if you take the external contour in white, you can measure what mass inside that white contour. So you have a mass, and then you can compute some kind of radius size that match that shape that you see here. So what we do and what most people do is to take the radius of the disk that has the same area as that cloud, right? Obviously, this is not a sphere. As you can see, it's not a disk, but that's a size measurement that is indicative of the area of your cloud. And then you can move up to the next contour, white contour, and you measure the mass within that, you measure the size, and so on, and you can derive a mass profile. For the velocity dispersion, we do something very similar. So we take, for instance, that contour here, the large external contour, and then we average the spectra within it. We measure the velocity dispersion, and we have velocity dispersion for a size. We move up in contours. We average the spectra in here. We measure the velocity dispersion, and so on. So these 13 CO spectra, for instance, that you have within these contours, you see that they change as you move up in contours. You can fit them, and you can get the velocity dispersion. So this is great, but there's one problem, though, that if we want to map the full profile, so this is the entire 40 parsec scale cloud, down to the clump at the very center on 0.2 parsec, you cannot use a single tracer. So for the large scale, we use 13 CO, which is a very good kind of low-ish density tracer. But now, if you want to get the velocity dispersion at the clump at the center, you need to change tracer. 13 CO is not good anymore, and we move to N2H+, which is a well-known tracer of dense gas. So for the mass profile, what we do is to get the mass is we use dust continuum on everywhere in the clouds, but we also need to use for some correction purposes, we also use 13 CO for the outer part. This is a detail. If you want to know, you can answer that. And then for the velocity dispersion, we use N2H+ at the center because N13 CO is not good anymore, and 13 CO in the outer skirts on the larger scale. So we have different tracers for different areas of the cloud, which is that we have to do. There's no way around that. So the sample that we used to do that study is 27 clumps, which come from our infrared dark cloud catalog. And we selected them so that they have a relatively narrow range of distances between 3 to 5 kiloparsec. A very large range of masses, 300 to 20,000. Also sizes, a few parsec, and aspect ratio. So here you have 4 examples, and you can see that some are very filamentary, some are more circular, and so on. And these are, then when we have the clump, that was our starting point, we look at in which molecular cloud they are sitting. And these are the 4 molecular clouds in which the 4 clumps I showed you before are sitting. And here we compute their masses, so 10 to the 4 to 10 to the 6 solar masses, diameters 10 parsec to 60 parsec, and so on. And so we have all the mass for our sample of clouds and clumps, right? The masses are estimated within its contours, as I said before, and we can compute, therefore, the mass profile. Now for the line velocity dispersion profile, as I said before, we take the contours, we average the spectra, 13 CO here for the larger scales, N2H+ here for the smaller scales. And then for the larger scales, like 23 parsec for that particular example, up to 0.3 parsec in that particular example, we have different spectra that we fit, and we get a velocity dispersion as a function of scale. We've tested a number of methods to see if we would be biased depending on the method we use to measure the velocity dispersion. Can talk about that if you're interested. And then we put everything together and we obtain something like that. So here's the mass profiles of our clouds. So that's radius versus mass. This is the mass measurement that we get from the larger scales. This is the mass measurement that we get on clump scale, where the star clusters form. And here we have the velocity dispersion versus radius. And this is the corresponding viral ratio, which is basically the combination of the you derive from a combination of these two profiles. So you see straight away there's a number of features that you see that that doesn't look quite right. The obvious one is the discontinuity that you see here between the 13CO120 measurement and the N2H plus 120 measurement, right? So N2H plus within the clump, as you go down in scale, you see that the velocity dispersion is flat, right? There's almost no change. Whether you take the outskirt of your clump at a few parsec scale, right? You do obtain around 1 point something kilometer per second velocity dispersion. But then if you just look at the center of that clump, then your velocity dispersion is almost remain the same, right? And that seems to be true for all the clumps that we looked at. Now, if you look at the cloud, your velocity dispersion is large on large scale and then tends to decrease, right? But in a certain way, so there are some variations depending on the cloud. But what is clear that when these two regions meet, the velocity dispersion that you will get in 13CO is far larger than what you observe in N2H plus. And when you combine these two into VRL ratio, obviously you have this discontinuity that you have here, transfers here, and you have these weird shapes where your VRL ratio increases as you decrease in radius. You have this kind of curved shape as well here, which is directly the result of the fact that the mass profiles are curved. So you have a number of features in there, that are a bit, I would say, strange at first sight. So what we wanted to do is to see if these features were real, if that's a problem of the methods, how we observe these clouds, and so on. So we want to disentangle what is true velocity and mass profiles hidden inside this data to what are the observational artifacts that come from the observations. So the way we've done that is by creating some simple modeling. So we had a sphere, right? We created a 3D sphere that we projected on the sky with a certain density profile, a 3D density profile, a 3D velocity dispersion profile with certain exponents, gamma for the density, beta for the velocity dispersion, and with some eventually some break or not in the parallel of these profiles. And then we projected that on the sky and did as we tried to observe so convolve this data with the same resolution as the observations and so on to try to see if and get the mass and the velocity dispersion using the same technique that we used to try to see if we were recovering the same features that we see on the observed profiles. So this is the same data I showed you before. Here in these two rows, we have in the background is the same, in the gray that you see in the thin line is the same here. The models are the yellow, orange, and red profiles. Right? So here are a certain set of models. So it is just single parallels in terms of density and velocity dispersion. And while here in those, here you have a break in the profiles. And this is mass profile, velocity dispersion profile, and VRL ratio profile. And you can already see that first, this large discontinuity that we were seeing between the two tracers also exists here. Right? You can clearly see that on the large scale versus the small scale, you have a large discontinuity here. You can also see that you have this curved shape that we also have in the data. And all this can be explained by a number of things. So the discontinuity here is just the fact that when you look at 13CO and you look at a sub-region within your cloud in 13CO, you are contaminated by gas, which is along the line of sight. So you're going to overestimate your velocity dispersion by a large factor because you are considering gas, which is not actually included within the 3D sphere of the gas that you are interested in. Right? You are contaminated, projection effect. And this, you don't have it when you're in N2H plus because N2H plus just pick up the dense bit. It's not contaminated by stuff that you have in front of the line of sight. So that's where the discontinuity is. Now, this curved shape is just to the fact that we use dendrogram to measure the mass, and that directly links to that kind of shape. I can go into details. So in order to best reproduce the data, the models, what do they need? They need a density profile that has a break. If it's just a single parallel, we cannot reproduce, especially the flat parts of that we see in N2H plus. So we need a density profile, which is typically R to the -2 in the center, in the clumps, but R to the -1 in the larger scale. And then a velocity dispersion profile, which is flat in the clump and scale as large on square root of the radius as you go outwards. So that seems to suggest that something is happening at some, radius. So we refer to that as a dynamical decoupling of the clumps versus the clouds, right? And if you believe those results, that means that star cluster formation is actually not a scale-free process. There's a scale in there that decouple your clumps that will then go on to form star clusters compared to what is going on the larger scales. So in terms of cell gravity, here what we have is the radius, again, of our clouds versus the virial ratio. And as measured in the clump scale, we're using N2H plus, on the larger scale using 13CO, and even on larger scales using 12CO. So that we got those points from the Miville-Deschênes sample. And what you can see is that energy equipartition, so clouds that are self-gravitating, bound by gravity, sit in this area here. Right? So that you see you have a shaded area is because actually that region depends on the density profile that you choose, right? If it's uniform, in fact, it's at a value of 2. If it's a r to the -1, it sits here. R to the -2, it's the limits between unbound versus bound. And so what you can see clearly is that all the clumps are by far, self-gravitating, there's no doubt about it. There are 13 CO clouds are also self-gravitating and up to, 20, 30 parsec in radius. And most of the clouds as seen in 12CO are also self-gravitating. So it means that here our clouds are self-gravitating on scales from 50 parsec scale down to the smaller scales. Someone really likes my talk. But remember in the introduction, I told you that Miville-Deschênes in themselves had found that most of the clouds were not gravitating. So how do these two things fit together? What we have here on this plot in orange is the Miville-Deschênes distribution, right? So it peaks around 3, and then you can see you have this very large shell of non-self-gravitating clouds. And our sample that I just showed you, which is shown here, sits there, right? This is it's the same values here. I've used the values for that plot here. I use the values published by Miville-Deschênes. So clearly, our cluster-forming clouds are biased towards lower virial ratios. Makes sense, right? To form stars, at some point, you need to be self-gravitating, you need to be collapsing. But this is saying that maybe most of the clouds in our galaxy might indeed be not self-gravitating, but those ones do not form star clusters, right? If you want to form a star cluster, your cloud needs to be in that area of the plot, which obviously makes sense. But at least here, we match the two, right? We understand what's going on. So our sample is biased towards low virial ratio. Okay, so what is our interpretation of what's going on? Our interpretation of the data is to say that these clumps, star cluster progenitors, are dynamically decoupled from the rest. I think this is pretty solid in my view, at least. And one explanation is that these clumps are collapsing while the rest is not. So the reason why I'm saying this is because the full cloud is self-gravitating, right? So you cannot have this decoupling cannot be due to a transition between non-self-gravitating versus a cloud which would be regulated by turbulence and not gravitating to a clump which becomes self-gravitating because the full cloud is self-gravitating on all scales, so it cannot be. And so the only thing that I can think of that would make this clump decoupled is collapse, right? But that would mean that the rest of the cloud isn't collapsing and therefore is maintained in some kind of balance through maybe feedback or something else. That I can't tell yet. Okay, so that's the profile energy balance part of the talk. Now, what we want also is if these clumps are collapsing, we want to be able to resolve the motion of the gas within the clumps and try to find evidence for such a collapse. So the way it's been done in observations, mostly using 3 different methods. So you can use absorption lines in front of a young massive star. So you have something very hot and you have gas which is pretty cold in front of it. And so you can have an absorption line. And this can give you a pretty good idea of what the inflow velocity is of your gas. This is quite reliable, but you need to have the right condition. And if it's too cold, too early in the collapse, you're not going to see anything. So there's not many data that allow you to measure an inflow velocity through that method. You have a self-absorbed blue shifted line, which is a very common technique. So HCO plus, for instance, is a very good line, optically thick. You have a very characteristic shape for a collapsing sphere when you observe it with an optically thick tracer. And you can fit that and get an inflow velocity. Some people here do that very well. So it's commonly observed. It's relatively easy, but the reliability is unclear. So there are some papers showing that even if your sphere is collapsing, you might not see that typical signature in those tracers. Now, another way to measure inflow is using velocity gradients. So this is very easy to do. The issue with that is that the interpretation is not unique. So you can have a velocity gradient that is due to collapse, but the same gradient could be due to expansion, depending on your geometry, or rotation, and so on and so on. So that's the issue with this one. So here's an example of a paper we published a few years ago where you have these nice filamentary structures, infrared dark, and you have the colors here show you the velocity of the gas, the size shows you the velocity dispersion, and here our interpretation of that was that you had flows of gas along these filaments and merging here, increasing the velocity dispersion, for instance. So you can try to do these kind of things. So recently, we tried to follow up some of the clumps that I showed you in the previous part of my talk with NOIMA. So we managed to map 7 of them. So at high angular resolution, typically a few arcseconds. I think that was maybe 5 arcseconds, something. In N2H plus in this distance tracer. So these are the 7 clumps, all infrared dark, because that's how we selected them. Here's this is Herschel, I think, 70 micron, yeah. And this is the N2H plus NOIMA integrated intensity of those clumps. There's a pretty good match. N2H plus is not perfect, especially when you have hot protostellar core at the center. So you have some mismatch between the peak in N2H plus intensity versus the continuum, but overall it's not too bad. But one of the main issues, and I'll show it in a moment, is that the lines are extremely complicated. And so we had to come up with a tool that didn't exist at the time. Now there are actually a couple that fit complex N2H plus line in an automated way. So we, and when I say we, I mean mostly Andy Rigby and Michael Anderson, came up with a code called Muidin that does that. So it's completely automated fitting. You give it a N2H plus 120 cube. It will fit with multiple velocity component the hyperfine structure of that line. So these are three examples. You see that it's a very complex line. To start with, it has a hyperfine structure. So you have multiple peaks. And then on top of that, you might have multiple velocity components. And then quickly, your lines become a bit of a mess. And this one actually not too bad. And so they developed that tool that fits everything, gives you your model, your residual maps, and so on. This code is publicly available here on GitHub. If you have N2H plus data you want to fit, I would recommend to use that. And so we fitted these NOIMA cubes, and then you can do a vast amount of things with these cubes. But you can do one of these plots, for instance, that's kind of, many people do that kind of plot now, where you have galactic latitude here, galactic longitude here, and velocity here. And so what we show here is the velocity of the best fit at each point in the cube. So the color here is the velocity dispersion. Purple shows low velocity dispersion, orange and red, and yellow shows high velocity dispersion. And then we project that as well on the sides, as you can see here, to have a better view of what's going on. So what you can already see, right, that it's a mess. You have some kind of filamentary structure in position velocity that seems to appear, some wiggles that have also been observed in detected in other observations. And and you have high velocity dispersion gas, low velocity dispersion gas, and it's quite complex. And this is true for this is one clump, but you have the same for the 7 clumps that we observed. Independently of the mass, right? The mass go from 400 to 2000 in that sample, so you have a factor of 5, but the complexity is almost the same in all of them. You almost don't see any difference in how they behave in this type of representation. Even seem in some cases, you even seem to have some layers, right? You have some kind of layering here of velocity. So you seem to have different flows and sheets that might be merging and converging together at the center of these structures. So there's a number of things that we've done, and the paper is quite long, and this paper here. But here I'm just showing one result from that paper, which is shown here. So here we try to distinguish the velocity from the core, so where individual stars or small star system will form, to the most massive core in these clumps, to the gas which is not in the core, which is in the more larger scale clump area. So in orange, you have the clump, and blue is the core, the most massive core, and here's the velocity dispersion of the gas within the core and within the clump in which that core sits for the different clump, for the 7 clumps. And there are some differences, but overall, when you look at the distribution between the core and the surrounding gas, it's quite similar how they behave. The velocity dispersion doesn't seem to be very different within the most massive core compared to the gas around it. And so one possible interpretation of that is that if indeed these clumps are collapsing, then gravity seems to drive a continuous flow, obviously, but that leads to a very chaotic structure and kinematics within these clumps, and that the core mass growth must also be chaotic, right? It's not like often we have this picture where we can identify nice single flows that will nicely merge to a nice core, and that doesn't exist in these things. It's extremely complex, extremely chaotic. It's a mess, right? But something is driving that mess, and because these structures are completely self-gravitating, in my view, that can be only one way, is that if that is basic gravity that just drive that continuously, that flow of matter at the center. And that I will finish with this last study here, which is the study of Michael Anderson, not published yet, but hopefully soon. So here it's a similar story than the one I just showed with Noima. We looked at a sample again. At this time it's 6 clumps. This time it's ALMA data. But here the difference with the previous study is that in the previous study, we focused really on the central parsec of the clump. Here we did mosaics that are slightly larger and also focus on the filaments that tend to connect to the center of the clump. So here we have what we call hub filament systems. We have a central high column density region connected with filaments. You can see there are filaments everywhere here connecting to the central bit. So these are what we call hub filament systems. They form star clusters as well. Some people say they are often associated to massive star formation, probably not only to massive star formation, but also. And we map them again with, so this time is with ALMA in N2H plus. And here you have, so this is the Spitzer 8 micron, so you see them in extension, infrared dark clouds again. Here you see that's the ALMA continuum, and you see the different cores at 3 millimeter. And this is the integrated N2H plus 120. So here it's 12 meter data, 7 meter data, and total power data combined together to create these images. And you can already see if you compare the extension here versus what you see in N2H plus, you have an excellent match between what you see in extension and what you see in emission in N2H plus. That was the purpose of obviously of obtaining this data. And here we did the same. We used Muidin, the code that I took before, and we fitted automatically all the cubes. These are an example of the spectra that you can get. So you can see that some are simple, but others are really complicated. And again, the same kind of representation with galactic latitude here, longitude there, velocity here. The color is the velocity dispersion of the gas. And so just by looking at this cube, actually, you can already see here it's dark, right? The filament seems to be dark. Dark means low velocity dispersion. But then when you get to the center, which is typically what we've seen with the Noima data before, velocity dispersion is very high and it's a mess. And we have this, again, the same picture for all the hub element system that we mapped. And so one of the things that we've done is try to look at the complexity of these gas kinematics as we go from the outskirts to the central part. And this is represented here. So as you look at only the velocity dispersion distribution in the outskirts, or in the filamentary part here, it's very low velocity dispersion, right? It's 1 kilometer per second, so this is 0.5 or something. But as you get toward the center, your velocity dispersion distribution starts to massively increase and shift to higher and higher values, reaching 4 or 5 or 5 or even 6 kilometers per second towards the very, very center, right? And this is another way to represent that, is number of components that we need in Muijing to fit the spectra. And you can, as you are in the center, you need a lot more velocity components to fit your spectra than if you are at the outskirts, where just one is often good enough to fit your data. So here the spectra, as I mentioned before, are extremely complex. You cannot, identify nice linear flows in these things. It's extremely complicated. You can identify the filaments in the outskirts, but as soon as you reach the hub part, then things get crazy. And we can see that in a slightly different way. So here we could say, well, you use Muijing data, Muijing fitting, so we don't really know what we are looking at. But here is just the data. There's no fitting. It's just the pure data. So that's the integrated intensity. And this is a position velocity diagram of those data, right? With position here, velocity here. The filaments in our hub are located here and there. You can see that. So you have 7 lines because it's a hyperfine structure. But you can see that it's very narrow here. These lines are very narrow and don't do much. They have a small velocity gradient that are, gently going toward the hub. But when they reach the hub, you have this massive velocity dispersion, and very complex kinematics and complex structure. And again, this is true for all the hubs, whether you have a 200 solar mass hub or a 10,000 solar mass hub, right? So this is a very common feature that we see in all of them. And again, the way we can interpret that, this is not a direct proof, right? But if we consider this structure, this hub element system to be collapsing, then the one possible interpretation is that these filaments, nicely, gently transport mass toward the center, but when these flows merge together at the center where most mass is, then it's being accelerated but not in a nice, simple way, in a very messy way. So that's the conclusion, and that will be the end of my talk. So the gas at the clamp center is extremely dynamic and complex. It's most likely transported from the outwards, inward through the collapse of this dense structure, and at least for hub filament systems through filamentary structures. And the core formation at the center of those is probably very chaotic in a way, due to the complexity of the dynamics which is there. Obviously, here again we have 7 and 6 sources, and in total it's 13 sources, so it's not a huge amount. So we are missing statistics, and that's where large programs with ALMA like Pantare that we're trying to get out with Alessio would be very useful. And I'll finish here. Thank you.
Nicolas, very beautiful talk. So thanks for question. So is there any question for Nicolas? I see a question there.
The profile, mass velocity expression as you did for the other ones for these particular?
Not yet, no. It's part of the plan, but I don't have them.
I see one question from Nana.
Very nice talk.
Thank you.
Like the slide where you show the fact that this
one?
Okay, this one. So we see you say that when you go from the outskirt toward the inner part, you see that the width of your lines is increasing, and also that the number of components that you need to fit the line is increasing. So I'm wondering if you measure the width of the single components. I mean, this enlargement is due the fact that all the lines itself are larger, or also because you have different components that can contribute.
That's a very good question. It's both. Right. So you cannot explain this increase of velocity dispersion by just the sum of individual narrow components that we just add up at the center. That doesn't work at all. You clearly have some that are on their own, the individual fitting components are much larger than whatever you see in the outskirts. In the outskirts, it feels like, you know, you're in low mass forming region nearby where you have low mass crystalline core. You look at the velocity dispersion, you get, you know, 0.2 kilometers per second. That's basically what you get on these filaments outside. But at the center, if you would add, basically you count the filaments and you would add them up, and you just cannot get that. It's not possible. I mean, I think you can almost guess that just by that position in this diagram. You have the flows coming here, right? That's your flow coming in of filaments, but then somehow they create something which is completely disproportionate to just the sum of these individual components.
And because we're looking at similar things in Amalgam.
Yeah.
You see also this increasing of kinematics complexity. Do you see also looking at the single velocity of the smaller structure? Have you never tried to see not only in terms of velocity, width of the lines, but also following the peak velocity that you see? Because you see in the y-axis, like the central velocity, no?
Yeah. Yes, indeed. Yes. Yeah. Okay. Yes. So you're asking me if
yes, on the
yeah. So
galaxy you see is the fact that the peak velocity.
yes, correct. Yes, the peak. Yes, you can almost. Well, here maybe it's not the best example, but on the previous one, I think it was clearer. Indeed, right. So this is the peak velocity that projected, right? And you can clearly see. I mean, you have this weakly filamentary structure individual that seems to be coming in all directions. So people like someone like, you know, Alvaro would see that. I mean, I've seen that and say, oh, you have fibers everywhere. I don't think that's correct at all. Right? I think you have more like sheet structures rather than that seems to come together. But I mean, it's very difficult from the data, it's very difficult to say one or another, right? We have projected data. But you cannot identify a nice single kind of fiber type of structure that people are seeing and follow it. I can't do it. I looked and I haven't been able to. So maybe I'm not doing it right. I don't know. But
of course, the structure.
Yeah, it's possible. I mean, well, they are different objects, but so yes, possibly they are different objects. But yeah, no, I'll be right.
I mean, the fibers are because they're near very extended. Also, Taurus is an example. Those are
I mean, yeah, they are. So I made actually the quantitative comparison in the mass profile of those clouds with Orion. Right. So the mass profile I showed right at the big so this even this one. So I tried to put RNA in that cloud using exactly the same technique, right? Identical. RNA fit at the very bottom of this cloud. But that surprised me because like this cloud, the lowest mass cloud, just have 200 solar masses of dense gas. Right? That's what they have. But actually in RNA, if you look at the mass, it's not very massive at all compared to that. So RNA, if you think of RNA as the most massive of the nearby clouds, you look at something like Taurus, right? I mean, it's a different mass regime at least. Doesn't mean that you don't have the same physics that lead the star formation in both, but yeah, there's a big step.
So there was a question from Alessio.
Thanks for the very nice talk. I have a curiosity about the last results of Michael Anderson. So you have NOIMA data, and you showed some.
Michael is the NOIMA ALMA data.
The ALMA, sorry, yes, about the ALMA. So you have compact objects that you showed here. Those are 3 mm compact objects.
Yeah.
No?
Yeah.
Only 9 H plus. I was wondering if you have the exactly velocity positions of these cores, and you have the position, of course, if you put them in your 3D
Yeah.
image, do they stay at the center of some of the complex filamentary structure, or they're just in the random position in this?
So we tried to do that. Yeah, Michael has done that. Well, first you need a tracer to find the position of the velocity of the cores. So N2H plus here, the thing is, if you take N2H plus at that position, right, you can have a mess, as I showed.
Exactly.
And then you identify which one of those is correspond to that core, you integrate it, you see nothing that needs really exactly matched what you see in this continuum. So it's hard to get. So now you need to have higher density tracer that we don't have yet.
Okay.
But he had tried to measure the velocity and see if you could see a trend and so on, and he couldn't. But there could be, because we don't really know what's the exact velocity of those cores.
So, if there is no other question, I have a question actually. I'm already intrigued. I mean, I really like your earlier results about the idea that there is a scale after which the dynamic of the couple, the structure from the rest of the car. And I think your data prove that this is a real promise. I just wonder, I mean, this is more a comment than a question for future work. This scale should be dependent on the properties or the mass or the internal clamp. So my question would be if there is any indication, even rough, from your initial data, or there is any plan to continue this, because I really think that this should.
Yeah. So that's the next thing. I understand what's going on, because so far I mean I don't know what's going on. Right? I have just an interpretation of what I see, but that might be completely rubbish, right? But what I think is robust is that indeed you have that decoupling.
Yeah.
Now you're understanding what causes it. So so there are really two things. I'm trying to first, the reason why I talk about RNA, and it's because I'm saying, well, if this is universal, surely should happen in RNA as well. That's the reason, right? And it turns out that it seems that it does. So you do see a same trend, but it's very early days, right? So I'm not 100% confident on that. But the difference is that it doesn't happen between 13CO and N2H plus, happens between 12CO and 13CO. So if that's true, that means it's not a density, which I thought initially, and we had talked with Alessio before as well. It's not, so the physics that leads to that decoupling is not necessarily then a density related thing, right? Because if it was, what you would expect is that would happen all the time in the same kind of tracer, because the tracer is a density tracer, right? It traces a certain density range. So the fact that we see it between 12CO and 13CO, it would mean that for RNA, it happens at lower density, but it happens at a similar scale. So it's a similar, so it would be a scale, whatever causes it. Again, it's very rough, right? But might be related to, it's a scale related issue rather than a density related process, which to me surprises me a bit. But it seems that in RNA, it's there. And now the other thing that we do is to look at simulations. So we have simulations of cloud-cloud collision, and we try to extract it, and then we have redshift transfer on that. We have N2H plus, 13CO. We construct the profile as we do, and try to go in the simulation to identify the physics that leads to that. So that we are trying to do that, but it's early days.
Sorry, just I want to continue on this. Just one question. When you say that you compare with RNA,
yeah,
the clamp that you went attention on the smaller scales is the KL nebula, I guess, the KL cluster.
Yeah, it's the integral shape. I mean, the densest part of the integral shape.
Yeah. But just a comment, in my opinion, if this is a kind of the comparison on that with the sample that you showed before, the sample showed before, it should be in much earlier stages, because KL already have developed a high cluster, and then possibly can be other contribution to your scale.
Yeah,
I mean,
it's possible. The thing is, we know a lot about RNA because RNA is close, right? We know not much about those because they are far away. So would we know? So if there was the same type of clusters as all as in RNA in the surrounding of those clouds, would we know about that? I'm not sure we would. They're galactic plane. I mean, it's visible. You don't see anything, right? So I don't know if I don't know. Maybe you're right? I just don't know.
So there were two questions. So Sergio's first, and then Gary.
I mean, what you just said rang a warning bell in my ear.
Yeah.
The fact that you said that you see evidence for another break when you compare 13 CO and 12 CO.
What do you say, other break?
I mean, you mentioned the difference behavior between 13 CO and 2H plus.
Yeah.
Then you say you see the same thing between 12 CO and 13 CO.
In for RNA, yeah.
Yeah. So to what extent this might be due again to different tracers? I mean, it would be nice to show this kind of break using the same tracer, right?
Yeah.
Can I comment on that?
Can I?
The FQS, because without.
I'm talking about this, yeah.
I mean, we see this break with FQS, looking at the 12 CO data, we see this break is exactly more or less at a few points, 0.1 parsec with the same tracers.
So here you have the same, it's a subsample.
Okay.
So it's the same data in West Plus and 13.0 in green and purple. The blue is 13.0322 from chimps. We couldn't do that for all of them because we didn't have the data for all of them at the time.
Okay.
And this is what we get, right? So that the 13.0 makes that's a good tracer because it makes that transition in a single tracer. As it says, if you look at the top left, which works well, they don't work very well, right? If you look at the top left,
Yes.
that one works extremely well. That's why the nice transition. This one does the transition as well. This one does the transition quite well. And others, right, seem to be flat. So one thing that we've seen in the simulation, doing the same kind of work with the same tracer that we obtained from Reggie Transfer, that the orientation might play a role. The way you look at your cloud, you don't necessarily always get the same profile. It might be related to something completely different. I don't know, right? But I mean, the tracer, obviously, that was our first, right? The tracer issue is obviously our first concern when we saw that. It's normal, right? I think we've done enough to show that that's not the case, but we probably need to do more. I would agree with that.
Sorry, one last question from Gary.
So actually, it was very related to this. I was going to ask, how do people try out using C80 to bridge the gap, either in the 1 to 0 or 2 to 1?
Well, we tried. I mean, it's 13CO, 202. We haven't. I mean,
because some sense I'm not completely. Am I sure that's bridging the gap? Like it was in 28 in the top left hand corner at the same physical size scale. You've got line width.
but you still have this projection effect that we explained with the models. It has to be there. I mean, if you look at it, if you look at the sphere, which is embedded within a large velocity, you have some gas. I mean, there's no other way around. You must have some gas around.
But you didn't do any attempt to background subtract from the nearby and see what's left.
I'm not sure how I would do that. How would you do that? I mean, in spectral line data. I mean, it's integrated. I don't know how would you do that? I mean, you can do it's what we've done, right? You can do the inverse problem, which do the modeling and see what you get. And that modeling shows that they are compatible. Obviously, it doesn't mean that's a solution. You can't. But it shows that if you do have that configuration where you are looking at a subregion within something which is larger in that tracer, you're going to be. I mean, to me, I don't see how it could be the other way, but you are contaminated by that large velocity dispersion gas. It has to be the case, right? And the models show that with a given density profile, given velocity dispersion profile, you do reproduce this and the magnitude of it, right? Not just that discontinuity, but also the magnitude of the discontinuity.
But if you have the big
Yeah.
ball of gas,
Yeah.
and then you have the denser things that you see only with 2H plus.
Yeah.
This contaminating gas with high velocity dispersion will be also here.
What is here?
Here, well,
I mean, you were thinking of a sphere, but you see that the geometry
On the
of
side.
is
Yeah.
on the side. So
Yeah.
I would expect there is some way to estimate the let's say the impact of this
Yeah.
more diffuse stuff
Okay, I
by
see what you
looking
mean.
at what happens in the surroundings.
Yeah. Yeah, I mean that's what
That's what I meant by
I understand what you
Like
mean, but I think that's what the model shows because you start from the outskirt where you have the stuff in the center. The largest scale measurement gives you the velocity dispersion without the contamination, right? And then as you go towards the densest bit, then you have more and more contamination, and that is included in the model. So I think it is there.
So I think this discussion can continue some
Yeah.
time. We are quite over the hour and so let's start. Thank you.